Okay, so in our last video, we saw that we can now combine multiple predictor variables for a better prediction, right? So both of those, both of the models with one variable by themselves, both of the simple linear regression models using high temperature and weekday have significant slopes. And the slopes are both significant in the model with two variables. So now that we can make more complicated models, right, lots of different ones, we might be interested in identifying, well, which of these complicated and not complicated models is the best model, right? How do we know if the model with high temperature and weekday is better than just the model with weekday or just the model with high temperature, right? We might be very much interested in learning that. And to talk about that, we're going to talk about the R squared associated with each of these models. Okay, so way back in week 3 and even a little bit last week, we learned about correlation, which is R, and we learned that correlation describes the strength of the variable. It turns out that it's more common to talk about the fit and how good the model is using R squared, which is literally just the correlation coefficient squared. Okay? That value, R squared, has a really nice interpretation, whereas R by itself isn't as nice. So R squared tells you the amount of variation in the response variable that is explained by the least squares line, right? So it tells you how much variation in Y, how much of the wiggle or the error or the noise can be explained by the least squares line. And another way to say that is how much of the wiggle in Y can be explained by the wiggle in X, right? We know X changes, and changes in X, it turns out, can explain some of the variability in Y, and the amount that can be explained is R squared. Okay, so if you were to take the correlation between high temperature and the volume, you would get a value of 0.583. If you square that value, you get a value of 0.339. So we can say that 33.9% of the variation in the volume of rail trail users and the number of rail trail users can be explained by the day's high temperature. Right? I want to point out, it says the least squares line here, but sometimes when we only have one variable in our least squares line, we just plug in that one variable in the interpretation. Okay, so that's one way to talk about how good a model is. I think we can see here, we want higher, right? We want to explain a lot of the variation. We want to be able to know where a lot of that change comes from, so higher numbers are better. Okay? So when there are multiple predictors in a model, saying the variation can be explained by the least squares line is the same as saying variation can be explained by all of those predictors together. And again, a good model is going to have a lot of variation, explain a lot of the variation, and will thus have a high R squared. Okay, so we've got a couple of different models now. I think maybe you can see where we're headed. We've got these R squareds. We know that high R squareds are good, right? So if we've got choices to make, if we've got a couple of different models, we may want to look at the R squared of those models. Okay, the way that you can do that is actually very easy. So remember, linear model LM, the function is very powerful. It spits out your coefficients, and if you take the summary, it spits out the standard errors and the t-statistics and the p-values. It also gives you the R squared. If you do summary of your model, $R squared, you'll get that value spit out to you. So we're comparing here we can compare here one model, the model with high temperature alone, that's got an R squared of 0.339, to the model with high temperature and weekday. That one has an R squared of 0.37. So we're explaining about 4% more, or I guess 3.5% more of the variation, which is good, right? We want to explain as much variation as we can. So if it were me, I would pick this model because this model explains more variation. Okay, now we've just talked about R squared, but we need to even go a little bit further. So we're going to change even what I just told you. R squared by itself is great when there's just one variable. It has that very nice interpretation. It behaves nicely. Once you start adding a lot of variables into the model, though, you run into some problems with R squared. Okay, we could add reasonable things. So we added whether or not it was a weekday. That's reasonable. That might actually help our response, knowing our response. We could add the cloud cover. We could add the rain. Those things would all be helpful. But eventually we would run out of reasonable things to add. Right? We could run out of reasonable things, and for some reason, we could start adding unreasonable things. So maybe we could add the score of the Red Sox game from the night before. Now, there's no real contextual reason to say that the score of the Red Sox game the night before would affect the number of people using the rail trail model at all. That just does not really make sense. But it turns out that if you add any predictor to the model, even if that predictor does not make sense, your R squared is going to go up, right? And so that's going to be a problem because we want models with high R squared, but we also want models that make good sense. We want reasonable models, models that explain the relationship. We don't just want to include things that don't make sense in our model. Okay? So what we do is use a new quantity for the adjusted R squared. Okay, I have the formula here, but basically what you need to know is that R squared, adjusted R squared, adjusts for the number of predictors in the model. So you can see over here, the K is the number of predictors. So if K is getting big, this denominator is going to get big and this whole thing will shrink. And so we want to adjust for that. So it's going to sort of balance the increases as well as the number of predictors. So the adjusted R squared is adjusting for the number of predictors in your model. That means you can't keep adding whatever you want forever and ever, because eventually there will be a trade-off between the number of predictors in your model and the gains that you're getting. Okay, how do we find this from our software? Again, turns out it's pretty easy. If you take the summary, it'll print out both for you, so you can do summary rail trail model adjusted R squared. That was for high temperature alone. The adjusted R squared for high temperature and weekday turns out to be 0.359. This is still an increase, so even after accounting for that additional predictor we have in our model, I'm still going to say that this model is better. Right? Now, a couple of other facts. The adjusted R squared is always smaller than R squared. Always, always, always. But again, you can still make comparisons on the basis of using that adjusted R squared. So there are times when having an extra predictor really helps, and it sort of overcomes the penalty from adding another variable into your model, and that's when we would see a higher R squared, adjusted R squared, and that's the model that we would want to use.